All right, 1 minute past 5. So welcome again, everyone. Thanks for joining in to today's start of our mini webinar series. We will host 4 webinars in a weekly mode. The first one will be on repetition on fundamentals of AES67, SMPTE 2110, particular transport and synchronization. Just as an outlook, next week we'll cover updates on standards and other industry alliances. The next week we'll have Daniel Bolt from Meinberg, who is providing an overview and, of course, updates on what is going on the precision timing protocol end. And our final webinar in 3 weeks from now is about remote production, and you will hear from Merging Technologies and Direct Out what has happened since our last series, which actually took place about a year ago. So, all right, today is about fundamentals of AES67 and 2110, in particular transport and synchronization. Just a quick note, if you have any questions, please feel free to pass them on using the questions tab, which you should see in your GoToWebinar control menu. We'll have reserved some time at the end to discuss any incoming questions. And of course, the recording of this webinar will be made available a day or two after this webinar concluded, and you will be notified, of course, by the automatic emailing system on the availability of that video. And of course, all the other recordings from our past series last year, summer, as well as fall webinar series are still online and can be reviewed. Okay, without further ado, let's just jump into today's session. So today we are covering transport protocols, of course. Well, basically RTP, UDP, IP, multicasting, quality of service, the RTP packet setup for anything AES67, particular audio, of course. The session description is an important object in the RTP transport domain. And of course, everything has to work together in sync, and that's where we use PTP, and I will talk a little bit about media clocking, stream alignment, and latency. So, as a preliminary remark, everything I'm discussing today applies in a very similar way to Ravenna AES67 and SMPTE ST 2110, because these standards all share the same principles, use the same protocols and methods for synchronization and transport of audio. Because, well, we are focusing on audio today, but basically everything also applies to video as well. So let's look at network transport first. It all starts with a network connector, with a network jack, or with a network patch cable. Now, if we look closer into the network cable or into the network jack, we will discover the 7-layer OSI, the Open Systems Interconnection Reference Model. Now, this is an illustration of those 7 layers, and I'm not going in deep detail into these layers. This is part of another presentation, of course, but some of these layers need to be explained a little bit further. So, on these layers, we typically see different standards and protocols working. And if we zoom in a little bit, let's just start with the layer 3, the IP layer. It's called the IP layer because IP is the predominant protocol working on layer 3. I'm not covering anything below data link level. Layer is usually Ethernet protocol, and physical can be anything, copper, fiber, or even radio waves. So let's see what happens on top of the IP layer. On top of the IP layer, there's the transport layer, and for anything AOIP, we are using UDP. Most of you will definitely have heard about TCP, IP. So what is the difference between TCP and UDP? Because both transport protocols work on the same layer. but they are, of course, exclusive to each other. So let's have a quick look at the TCP features. TCP is a secure transport protocol between any two connected network devices. Basically, a connection is created, and this connection, through the features of TCP, guarantees a reliable in-order delivery of all packets from the sender to the receiver. So there are things like checksums for segment error detection, sequence numbers, which can detect out of order reception of packets. And there are also, of course, mechanisms to request retransmission in case packets have not been received or have been timed out. So that on this layer, it is already ensured that every packet which needs to be sent from the sender to the receiver is actually arriving at the receiver. Now, the big disadvantages, or the big disadvantage of the TCP protocol is that it has unpredictable delay characteristics because of its built-in retransmission feature. So it's clearly understandable that incoming data needs to be buffered and checked for completeness and retransmission, and then sorting in the retransmitted packet into the right order and so on. And that all comes with certain delays, of course. So that certainly is not very suitable for real-time communication. And I mean real-time communication in the lower milliseconds range. So the alternative we have is UDP. UDP is a simple, unreliable datagram transport service. It's called unreliable because it does not have the features like TCP, so it does not provide reliability in terms of packet delivery or ordering guarantees. Datagrams or packets may arrive out of order or even go lost, but it has at least a checksum for detection of packet bit errors. However, it's much faster and more efficient for our time-sensitive purposes. So it's the obvious choice for anything real-time audio and or video transmission. By the way, it's a quite old protocol. It originates back into the early 80s. All right, one layer up. On top of the UDP protocol, we use RTP protocol on the session layer. RTP is the real-time transport protocol. Here's a view, a simple view onto the RTP packet. It has an RTP header, which is actually 12 bytes. It has an optional header, and it has a payload area. That is a simple construction of the RTP packet. When we combine RTP over UDP over IP, we have to add overhead for the IP and UDP packet headers. And together with the RTP overhead, we have a total of 40 bytes of overhead for each payload we want to send out. So IP header, UDP header, RTP header have a total of 40 bytes. And then, of course, it's a certain amount of payload which travels within each packet. So regardless if we are sending just a sample, a single sample, or a bunch of samples from a bunch of channels, we always have 40 bytes overhead per packet. And we have another limitation which originates from the most commonly used layer 2 protocol. What we are using nowadays, that's the Ethernet protocol, which has a 1500 bytes maximum transfer unit for its payload, and as IP, UDP, RTP are transported in the payload area of an Ethernet frame. We have a remaining size of up to 1,460 bytes for any audio or video payload per packet. And I can tell you, we definitely want to avoid jumbo frames because that would most often translate into packet splicing. And that is something which can get very, very ugly for certain reasons. And so a rule of thumb is we never want to exceed the MTU of the standard Ethernet frame, which is 1460 bytes of payload for audio or video. Let's have a quick look at how this looks on the cable. Looking at the Ethernet frame, of course, here. So we have an Ethernet frame, which has its header and its trailer, and we have the Ethernet payload. Here are the size numbers. So the maximum size we can have for an Ethernet frame, depending if it's running with VLAN tagging or not, is 1518 or 5022 bytes, which results in a net payload, Ethernet payload of 1500 bytes. And into this payload, we squeeze the IP packet, subtracting the header. There are 1480 bytes IP payload remaining. Likewise, the UDP framing goes into the IP payload. That has another 8 bytes of overhead, so we have another size for the UDP payload. And finally, the RTP packet travels inside the UDP payload. So there's our final audio or video data or whatever we want to transport within an RTP packet. So that's the remaining 1460 bytes. That's what we could see or can see on a Ethernet wire. If you are using Wireshark, you can exactly identify these different blocks. So here's another view onto the full Ethernet frame with an RTP protocol sitting inside, and you can see among all these different header data, there's the audio video payload. Right, so we have that packet now, and we have different ways of transporting this packet across the network. And the obvious way of transporting RTP packets for our application, at least, is multicast. So what is multicast? Well, multicast is in contrast to Unicast. There's a third method, which is not very viable for any sort of audio or video data transport. This is broadcast. So let's discuss multicast versus Unicast, because these are the mechanisms which are used in certain real-time applications. So let's assume Unicast. Unicast is a point-to-point connection between a sender and any receiver. Well, that means that any additional receiver would add another individual connection on the sender side. And that in turn means network traffic increases with every additional Unicast stream. So here's the picture. We have our little network here, a sender, 3 different receivers connected via a network. And so the sender is sending out the first stream to the first receiver. If the second receiver wants to have maybe even the same data, the sender has to create the very same data stream, but towards a different address. And that means if another receiver comes on, we have an increase of network traffic, particularly on the sender side. So the further we go towards the sender, the more increase of traffic, or in other words, the more bandwidth need we create with unicast transmission. So apparently the scenario where we want to use unicast is whenever we have individual streams to be transferred between any 2 devices. For example, let's say a multi-channel stream or a already produced program stream between maybe 2 remote locations or anything like this. So if we have a larger network with multiple signal sources and potential receivers, we probably want to use multicast, which translates into one-to-many transmission. So one-to-many transmission means that we only have 1 connection per outgoing stream on the transmitter side, and with the help of the switches in the network, any interested participant can join in and subscribe to an existing multicast stream, and the protocol which is being used for subscribing to available multicast streams is called IGMP, Internet Group Management Protocol. And here's the picture how this works. Again, we have the sender that is creating 1 single stream. As long as no one is subscribing to the stream, the first switch is actually dumping the data or is not forwarding the data. So it's just transmitted from the sender to the first switch. As soon as there's an interested receiver, it sends out an IGMP join command to the adjacent switch or to the connected switch, and that is forwarding the IGMP join request into the network, where it reaches that particular switch, which already knows about the requested multicast stream. And then in turn, the switch starts to forward the multicast data along the path where the IGMP joins have been received. So here's the first receiver connecting to the multicast stream, and this pretty much looks like a unicast stream. And actually, in terms of bandwidth need, a single multicast connection has no drawback compared to a unicast connection, except for that it might be a bit more difficult to route multicast streams between different network segments or different corporate network environments. Now, then if multiple receivers are requesting the same stream, the sender is not setting up multiple streams, but the switches who already have these packets are copying the packets to the particular egress ports. So here's the second receiver requesting the same stream, and that switch knows that stream data already. So it's starting to copy the packets onto the next or to the other port and forwarding the stream packets, just as it is done with the first receiver who was interested in that particular stream. And naturally, if the third receiver comes on, the IGMP mechanism is used again. And as we can see in the illustration, that the network load is really minimized because that IGMP join is only forwarded to a switch which already knows this traffic. So in this particular example, the IGMP is not forwarded to the very first switch, but to the second switch in a row, which already has the stream data, and that is then copying the packets and forwarding it. So as you can see, regardless of the number of receivers subscribing to the same stream, the network load stays minimized at every individual link in the network. So this is the natural scenario where we have a single source which needs to be distributed to many potential recipients. Right, here's another view on this, just as a quick overview. We have the Unicast situation on the left side, where we have the same data distributed several times from the sender to the receivers. On the right side, we have the single data stream, which receives all the interested receivers in multicast mode. So that's the transport. And now we have a closer look on the packet setup. So what is actually living inside an RTP packet? So the encoding packet setup, for this example, I'm using the AES67 minimum requirements, or the definitions for AES67, which need to be fulfilled to actually set up an AES67 stream. Well, first of all, we talk about the media format. The media format is linear postcode modulated data, so linear audio data with either 16 or 24 bits. So both need to be supported in an AES67 environment. Then per stream, we can have a channel count between up to a maximum of 8. So any number of channels is valid up to a maximum number of 8. Of course, we can send more channels in a particular stream, but that is outside of AES67. Ravenna can definitely deal with more channels than that, but this is the minimum requirement. Keep in mind, AES67 is an interoperability definition, so we have set up a set of minimum viable requirements to be AES67 compliant. So per stream, we can have up 1 to 8 channels, so a stereo or mono stream, a stereo stream, or a surround stream are perfect setups for a single AES67 streams, either in 16 or 24-bit linear PCM. Sample rates. Of course, sample rates are very important. And as 48 kilohertz is the predominant sample rate or media clock rate used in professional applications, that is the only required sample rate to be supported. But AES67 also mentions 44.1 as it is relatively widespread, and also 96 as it is being used in some professional applications. So it doesn't require those, but it mentions them and gives a recommendation if you want to run your AES67 device in 44.1 or 96, and if it's supported by the device, how the packet setup then has to look like. Optional recommendations. The packet time, the only single packet time is 1 millisecond. So what's the packet time? The packet time basically reflects the number of samples per channel at a given sample rate. So since 48 kilohertz is the only mandatory sample rate, AES67 concluded on 1 millisecond packet time, which means that per packet there are 48 samples per number of channels in that particular stream. So anything from 1 channel, which means 48 samples, up to 8 channels. I can't do the math that quickly, but that would 8 times the number, 48 samples per packet. Again, AES67 also mentions other packet setups with 6, 12, 16, or 192 samples per packet, resulting in packet times like 125 microseconds up to 4 milliseconds for particular applications. These are optional definitions or recommendations, but are not mandatory requirements. Finally, we have set forth a maximum payload size of 1440 bytes. Recall what I've said earlier, a few slides earlier, 1460 bytes is the maximum possible payload size with IPv4. We have had a closer look at IPv6 already, and due to the larger size of headers which are required, there's a remaining size of 1440 for the net payload, and so we limited AES67 streams with a quick look into the future to carry only 1440 bytes of payload within AES67. So here are a quick example. So that saves me the math. Actually, as you can see, a simple stereo setup at 48 kilohertz will result in 192 bytes of audio payload, and multi-channel, 8-channel surround setup with the same sample rate has close to the maximum payload size, still fits in there. And if you have, for example, a situation where you can reduce the quality to 16 bits, 2 channels, and want to have a relaxed packet time for a lower packet rate, you can use 4 millisecond packet time. This is 192 samples with 2 channels, 16-bit. That is 768 bytes. These are just examples of valid packet setups within AES67. Now, the big question is, how does a receiver know what is actually in the payload if there's a range of things which can be packetized into the payload? Well, if you look again at the RTP packet, at the standard header, there's a field called payload type. This payload type field here consists of 7 bits. So basically, it can contain any number between 0 and 127. And actually, the IETF, which is the Internet Engineering Task Force, which is responsible or in charge for defining RTP, they have started assigning static payload types, starting, of course, with index 0 and going up all the way. And once they, were half through the process, they thought, okay, this is not going to have a very good end. We can easily identify more than 127 different payload types. So they actually stopped at assigning static payload types at 95. And introduce something which they call dynamic payload type. So that means any payload type number beyond 95 does not point to a defined payload anymore, but is a so-called dynamic payload type which needs to be defined elsewhere. Now, if we look into the static payload types, there's only one payload type which can be used for professional broadcast or audio quality, which is linear 16-bit at 44.1 kilohertz. But anything 48 kilohertz or 24-bit is not part of the static definitions. But if we look into further RFCs, further definitions by the Internet Engineering Task Force, we luckily enough have L16 and L24 defined as particular payload formats. But then there's also the AES3 payload format, which most of the audio engineers know and use in certain applications, but AES3 does not have a payload type definition yet. And so from the Ravenna side of things, we simply define something based on a well-known format from the old days of Firewire, the AM824 format. So we particularly managed to define this format without breaking any compatibility limits. And it turned out that later on, when SMPTE took up on the AES3 format, that this became an official standardization within SMPTE 2110-31. Basically, the whole SMPTE 2110-31 format or definition or standard is based on the Ravenna AM824 transport definition anyway. So, as said earlier, if we see a payload type number 96 or above, there needs to be an additional information to be transported to the receiver so that the receiver exactly knows what is in the payload area. And this is done through the session description protocol. So what is session description or the session description protocol? This is another standard defined by the IETF RFC 4556. And this SDP basically is always required to describe the stream formatting, the synchronization, and also provide connection information to a particular stream. This needs to be provided by a sender or its related management instance for any particular stream. Otherwise, the receiver won't know how to connect to the stream or doesn't know or won't know how to actually decode a particular stream and how the stream is actually being synchronized. Luckily enough, the SDP is a human-readable text. So this is an example of a simple SDP file for AES67. We have information in there of the originating device with its IP address. We have a string, which is can be a title or the name of the stream. This is just could be anything. It does not have to be unique, so it's also an optional parameter actually. Then we have information about the synchronization of the streams. The first marked line is the reference clock it's referring to. We will jump in a minute to PTP. So this is basically describing the grandmaster from which the media clock of the sender device, which is emitting the stream, has been synchronized to. And also there's a media clock information which tells the receiver what is the relationship between the media clock and the reference clock. Then the other important information I mentioned is the payload type. First of all, the M line describes its audio. It's on port for 5004, and it relates to the RTP AVP format, which this is the standard description basically for audio payload. And here's the magic payload type number, 98. So 98 is what is then in the payload type section of the RTP header. So there would be a 98. And through the SDP information, we now can decode through the next line, okay, 98 in this particular case means it's a linear 24-bit stream with 2 channels at 48 kilohertz. So this could be L16 at 44.1 with 8 channels or whatever. So through these 2 lines, a receiver exactly knows what is the formatting and encoding in the payload area. So regarding connection information, this is the information on which multicast address this stream is actually living. So now the receiver knows if it's interested to receive or subscribe to this stream. It has to issue an IGMP join request for this multicast address. And then the switches, who are not particularly interested what they actually transport in their multicast streams, but they know the multicast address. And if they receive an IGMP join with this address, then they start forwarding any packet which is destined to 239 and so on the related port. And here's the final one, the packet time. It's in milliseconds. So the packet time of the streams is exactly 1 millisecond. And since it's a 48 kilohertz stream, it exactly has 2 channels times 48 samples with 24 bits in it. So that's the secret behind the SDP. As I said, it's human readable, so you should be able to retrieve that from any sender and look how a particular stream is being set up. Final thing for transport, what is important is the quality of service. Quality of service, what is that? Well, quality of service, everyone knows that. The annoying thing, if you're lining up for an airplane, if you want to board an airplane, there are at least 3 queues, the first class, business class, and economy class. And what it actually means, first class is allowed to board first, then business class, then economy class. Once economy class boarding has started, any business or first class passengers can always jump in between and is the next one who is allowed by the egress scheduler to cross the bridge into the plane. This is exactly what differentiated services, quality of service mechanism is following, and that is actually supported in any managed switch these days. So I'll jump quickly over this because it's quite clear how this works. Basically, The idea is that every IP packet receives a DSCP value in its header classifying the particular traffic. So if we look again at the at the full frame, the full layer 3 header is just this section, and inside the IP layer 3 header, there's a field called type of service, which has been redefined a while ago by the IETF to contain the DSCP, the differentiated services code point, which is a number between 0 and 63. The number itself doesn't express any priority. It has to be assigned to a particular class of service. Here's an example. Let's assume that a switch, a number of streams, they are called flows here, arrive. One of those streams has a particularly high priority class marking. It's called CS6 that relates to a particular number. We have expedited forwarding on 2 streams, advanced forwarding, and all the other traffic, might be email, web browsing, whatever traffic, has best effort classification. So then the switches store those packets in different priority queues. Here's the priority queues again: first class, business class, economy class. So we have queues in the switches. Usually we have 4 of them in a managed switch, but larger switches can also have 8 or even more priority queues. And then there's the classifier, which basically looks at the particular DSCP tags in the packet, and then according to its configuration forwards the individual packets to the particular priority queues. That's just showing your ticket, and okay, you can go into the first class queue. So CS6 is assigned to go into Q1, expedited and advanced forwarding into Q2, and best effort has to gather in the lowest priority queue. And then there's an egress scheduler, which actually is allowing passengers from the queue onto the bridge to the airplane. So it's forwarding packets to the egress port onto the actual connection. And so the scheduler would always look, is there a first class passenger waiting in line? So that one is allowed to go first. If there's no first class passenger, what about the business class passengers? Okay, business class passenger is next, and so on. That's the way how QoS actually works. And one important thing is it needs to be supported along the full path or the whole network from the transmitting to the receiving end, because if it's not configured in the same way in all participating switches, things can happen just like in real life. You have a first class ticket on Lufthansa, and then you arrive at American Airlines with your first class ticket, and it's only worth for economy class because it's not the same configuration. It's not acknowledged there. So make sure that you're traveling on Star Alliance all the way through, because that has the same configuration all along the full traveling path. Important to know, there is no admission control, so any congestion or packet drop-in is still possible when bandwidth is exceeded. So in other words, again, flight examples from travel, if the flight is overbooked, not everyone can get on the plane, and of course, who is dropped first? It's the economy class passengers. So the best effort packets are dropped first. That's how QoS actually works. All right, on to the next very important block, which is timing and synchronization. Well, synchronization and media clocks in AES67, 2110 or Ravenna just work the very same way by all nodes running local clocks. Local clocks are precisely synchronized to a common reference clock using the PTP protocol. PTP, Precision Time Protocol. We all know that we have a PTP version 1 standard being issued in 2002, another one which followed in 2008, and the ugly thing is both are not compatible. In practice, what happens is we have Dante working on PTP version 1, we have AES67 working on version 2, and they are not natively compatible, so you need to have some sort of bridging or boundary clocks in between, which translate from one protocol to the other, and you can at certain times have both protocols running on a network, which has provided some confusion in the past, but now that people are knowledgeable about that, this can be set up to work concurrently on the same network if you know what you're doing in the network configuration actually. So once we have synchronized local clocks, they can generate media clocks as desired independently from each other. So this is how it looks like. We have a master clock, may or may not be connected to GPS. If it's connected to GPS, we know it has the same reference as other master clocks worldwide. That is very handy for streams which need to cross continents or larger regions. But if it's not GPS, it's running basically on a precise clock. Then we have all the participating devices with their local clocks built in, and these are disciplined through the precision time protocol to actually follow the master clock very, very precisely down into the dual-digit nanoseconds range. Now, once all these clocks are precisely enough or accurately enough synchronized, you can tell them to generate a media clock. And if you tell a particular device to generate 48 kilohertz media clock, well, it will definitely be the same clock at all devices as long as these clocks are accurately enough synchronized. So in other words, if you look at these media clocks on an oscilloscope, they will have the same frequency and the same phase. So media clocks are not distributed, but generated locally through distributed time. Now, it's clear that with this principle, I can generate any desired media clock, let's say 44.1, 96, even 90 kilohertz video clocks, whatever, and that the network is actually possible of operating with different media clocks at the same time because the network doesn't care. Of course, it's not possible to receive a 48 kilohertz stream with a receiver which is told to work on 44.1 without sample rate conversion maybe. But if you have two different receivers running on 48 and two other receivers running on 44.1, they can concurrently use the same network without any interference. The good thing is all these different media clocks are always synchronized to each other. They are coupled, they stay connected. Phase accuracy requirements of AES11 can easily be met. You might have to deploy PTP-aware switches in between. I'm not going deeper in this, but we have boundary clocks and transparent clocks, which increase the precision and accuracy of the time distribution via PTP on a particular larger networks. And if you need to synchronize across different facilities, I just mentioned that, go through GPS with international atomic time, and then you have this very same time in different areas throughout the world. Now, then the next important thing is if I have the media clock and if I have absolute time in my devices, and they are all the same actually, then I can intake an audio stream or audio data, and any audio sample I'm taking into a particular device receives a particular timestamp which tells the system at what particular time of the system that media sample has been taken. And since time is the same at any place on the network, every device can easily identify when a particular sample had been taken, regardless how far it had been traveled on the network. So how does this look like in an RTP packet? Well, here's our RTP packet again. We have the RTP header and the payload data. And inside the header, there's a 30-bit field, 30-bit wide field, which is called timestamp. And with our particular audio format, linear PCM audio, the IETF has defined this timestamp field to be a media clock counter. So in other words, it is counting the media clock cycles from the beginning of time, from the origin of time, and is exactly marking the number of media clock counts which have been passed since the origin for the first sample in a particular payload field. So in other words, if I look at two consecutive RTP packets, let's say with 1 millisecond packet time, the timestamp of the first packet would have a certain number, let's say, just for the sake of it, 1000. And the next packet would carry a timestamp 1048. So since 48 clock cycles have passed between the first sample in this packet and the first sample of the next packet. So that's how it actually works. Here's a diagram of this. Again, we have sender and receiver. We have the reference clock, which is the PTP grandmaster. We have the local clocks inside the devices. They are disciplined through PTP. So local clock is an exact copy of the reference clock. we generate the desired media clock from the local clock, let's say 48 kilohertz. This is, of course, also be done in the receiver in this particular example. And then we generate the stream data with this media or sample clock, generate the RTP stream, which is connected to this particular media clock. But the RTP timestamps inside a stream may carry a particular offset. I'm not explaining why this is the case in RC3550. It's just the case. It can have a random offset. So for the receiver to actually know when it's receiving and looking at the timestamps of a particular RTP packet, when this has actually been generated, it needs to know this random offset. And that is, again, transported in the SDP, in the session description protocol, with this magic line, media clock, direct, and the offset number. So the offset R is transported in the SDP file, so the receiver perfectly knows when a particular sample of any particular packet, RTP packet, had been generated on the receiver, on the sender side. Now, SMPTE2110 has a constraint on this. It just says, okay, we don't want to have this random offset. We don't understand why our IETF has designed this random offset, or if we understand it, we don't need it, we don't want it. So we require that the offset is 0. So this line actually is required, but always carries a 0 in this particular line. So that means that all streams are perfectly aligned with respect to the grandmaster time without any further calculation in between. So that is the picture how timing works inside of AES67, 2110 Ravenna. Now, the next thing we want to have is a fixed and determinable latency, or what we call it link offset between any two devices. Sometimes it's also referred to as the playout delay. So here's another diagram illustrating the playout delay. So we have a sender on the left side. Let me bring up the laser pointer. So we have a sender on the left side. We have the network in between, and we have a receiver on the right side. And the sender has its sampling stage or analog digital converter or whatever it has. The receiver has another output stage. In this case, it's a digital analog converter. And we have defined the reference time planes at the point where a particular audio sample is forwarded from the sampling stage into the network packetization or sender network system side. So at that particular point in time, it receives the RTP timestamp or the media clock cycle count. And then this is fixed and travels across the network, and regardless how long it takes, it still has the generation point in time when it is being depacketized and processed by the receiver, and through a selected link offset, we can make sure that it is exactly played back at a particular time after it has been generated at this point. Of course, the link offset we choose needs to be large enough to cover, any delays which happens inside the packetization system of the sender, inside the network, particular packet jitter, and these kind of things need to be taken into account, or the size or distance of the network, and also any processing inside the receiver network system before it actually is being forwarded to the output processing stage. So that is the link offset, and it has defined time planes which cover for all these various delays. Now, the calculation behind this is also very simple. We have the RTP timestamp of the first sample in a packet. We add the selected link offset to that particular packet. We subtract any RTP offset, which may be transported with the SDP offset information here, and that results in the desired playout time for a particular sample. So in other words, if you look into the, let's say, delay time of a Ravenna receiver, if you enter 2 milliseconds or 5 milliseconds, that calculation and the system behind it always makes sure that any particular sample is exactly played back the chosen link offset time or playout delay. That's the mechanism behind the link offset. All right, and then of course it becomes clear how inter-stream alignment can be achieved. That is simply by comparing the timestamps, the playout, and the desired playout times, and relating those to the individual essence data. So here's another diagram illustrating this. Let's see in this example, it's a video flow which is running through various processing stages, a mixer, whatever compressor, I don't know, and it finally arrives at a display. Let's bring the laser pointer on again. So camera, mixer, processing device, and final output device, a display. And we also have an audio stream, which originates from a microphone, passes through a mixer, and finally reaches a speaker. And although these streams are living independently on a network, individually processed, and have individual playout devices, they can be aligned, yes, by simply telling the speaker device that it has to delay the playback for a certain amount of time in order to match the later arriving video information on the display. So in other words, the speaker would need to buffer its incoming audio data for a while before the related video data arrives at the display and is being presented onto the display. Now, how this is well, actually, these buffers are there in every network device for good reason, because at every stage, you need to cope with any particular packet jitter, which may have been accumulated through network transport or other processing mechanisms. So in other words, every device has this on its input stage. And how do you relate this across a complex operation? Well, in this case, there's a broadcast controller. This broadcast controller needs to be aware of the various individual processing times, or the time a particular information, audio video information, requires from its ingress time plane to the egress time plane. So that information needs to be known by the broadcast controller. And then the broadcast controller can calculate the traversal times for a given sample from the camera to its final display destination, or from the microphone to its final speaker destination, and can tell each of these individual stages what appropriate playout times or forwarding times, delay times are required in the system. All right, final word on latency. Always people think IP systems always have huge, big latencies. By now, you should know that this is not the case. Latency, of course, is something which we definitely have and cannot just ignore. So the underlying network technology contributes to latency. If I have fast Ethernet, gigabit Ethernet, or even faster network infrastructure, of course, with faster network infrastructures, the latency, inherent latency decreases. The network topology, number of hops or distance, if we talk about regional or worldwide distribution, definitely contributes to latency. And the network jitter, switch performance, the number of hops again, the bandwidth utilization on a particular links, competing traffic, and QoS in general. These all may contribute to latency in the network. And of course, the packet setup, stream configuration, the packet setup, samples per packet, the sample rate, they all go into latency. There's a simple spreadsheet which is available on the Ravenna webpage, which gives you the idea what minimum latency, for example, at a particular frames per packet or packet size will have. So if you have a 1 millisecond packet time, it definitely tells you can't go below 1 millisecond of latency, because the packet has to wait for all the 48 samples coming in. And that means for the first sample, well, this is already 1 millisecond ago when it was being gathered, before the packet even gets onto the network. And so that means you can't go below the 1 millisecond line. As I said, there's an Excel sheet on the Ravenna website. For those who are interested in playing around with a few numbers, just go there and download it. Okay, we have this highlighted here again. All right, baseline definitely is if you have a performant network, if you use decent packet times, let's say just 6 or 12 samples per packet, it's not magic, it's not big magic to achieve sub-millisecond latencies even in a layer 3 packet switching network. So that concludes the quick run-through of the fundamentals on AES67, SMPTE ST 2110, and Ravenna transport and synchronization. And now I would be up now for some questions. And for this, I want to bring in my assistant, which is who is Roland Hamming. Roland, can you go online now? Yes, we're already online. So Roland, what questions have been accumulated meanwhile?
Well, to start off with, we have a question from Massimiliano, who asks, can the sender also be the PTP Grandmaster?
Yes, absolutely. When I was saying a grandmaster needs to be on the network, I didn't mean that necessarily a particular device or a dedicated device has to be on the network. The mechanisms of PTP just work. Sorry, just work like it is actually the PTP scheme is actually looking for the best available grandmaster on a network. It's called the best master clock algorithm, and most standards have the capability to act as a grandmaster if no better grandmaster is being identified on the network. So there's an automatic scheme built into PTP which determines the best available grandmaster. And if there's no dedicated PTP grandmaster device, a sender will take over or will take the role of the grandmaster.
Okay, that's great. If anybody else has any other questions, they can type them into the question box, and we will ask them. And one question I wanted to ask Andreas is, if I have a Ravenna device, how can I be sure that it's going to work with ST2110, which is a newer, obviously, thing on the market? We're talking about ST2110-30 instead of just pure AES67.
Yeah, the good thing actually is Ravenna was out before AES67 was standardized. So when AES67 concluded on its standard, everything which was already in Ravenna, no, the other way around. Everything AES67 defined has already been part of Ravenna. So the whole synchronization, transport, and payload setup and everything, even the signaling of the stream formatting, etc., is fully compliant with AES67. So Ravenna automatically, inherently supports AES67. And even better, when SMPTE they defined the -30 standard for audio transport, they were wise enough not to defining or inventing the wheel twice or the wheel over and over again. They looked at any existing standards and they identified AES67 as an interoperability standard already being widely supported in the industry. And so they decided to basically copy the fundamental ingredients from AES67 into the -30 standard. Actually, they are referencing AES67. Well, and since Ravenna inherently has AES67 integrated, it is already SMPTE 2110 compliant.
Okay, that's great.
Well, and to add on this, I mentioned that earlier, SMPTE, since AES67 can only transport linear audio, linear PCM audio, just like L16, L24. But in the audio world, we also have AES3 as a very popular format, which has additional metadata or even the capability to transport other non-linear audio formats like Dolby E or even non-audio data at all. And this goes all on an AES3, three-wire connection or two-wire connection or through MADI. It cannot be transported with AES67, but Ravenna has identified this as an important format and has already defined the AMA24 format. And then again, when SMPTE looked at this, they identified, okay, we need AES3, AES67 doesn't cover it. So is there anything out there which already covers this? And we said, yes, it's Ravenna and it's being used. And so they said, okay, let's just copy all these things over and make sure that whatever we define in -31 is in line with the existing Ravenna AMA24 scheme. So that's why Ravenna is also ST2110-31 compliant.
Okay, that's great. Well, we have no other questions coming in, but I have one more, which is just when is the next webinar?
Right, so before I jump to the next webinar, I just want to give you a few more hints on available resources. Ravenna-network.com, our Ravenna website, always has some very valuable information available, not just about Ravenna. So we have sections for AES67 and 2110 for those who just start their interest in anything AOIP. And of course, we have an extensive resource section where you find very, very valuable material like, white papers, explanations, connect manuals, even free software in the resource section. And if you want to stay online with what's going on, we every 2 to 3 months we issue a newsletter. So please go ahead and subscribe to our newsletter on the webinar website. We promise we won't spam anything. It's just, well, as I said, 2 to 3 months per newsletter with new stuff. And of course, as I said in the beginning, the next webinar in our short series is coming up in 1 week from now. And that is about a status update on standards and various industry activities around AES67, 2110, and so on. So if that's of interest for you, please register. Again, the webinar website has a link on the homepage where you can register for this and the other 2 upcoming webinars. And of course, the recording of this, as well as the other webinars, will be available in a day or 2 after processing it, and you'll get a notification. Further question, Roland, or is that?
No, that's it. That's where we are.
Okay. So then, basically, that's it. We even finished a few minutes before the hour, which is very rare with me, I think. So thank you for watching. Thank you for joining us, and hope it was of some value for you. And we'll love to see everyone back next week, same time, same place. Thank you, and goodbye.